Hey, what's up everyone, and welcome back to CS AI TTL, your home for mastering data structures and algorithms. I'm your host, and today we are going to tackle one of the most fundamental ideas in all of software engineering, the cost of code. When we write code, we are asking the computer to spend its resources. The two primary resources are time, measured by the processor, and space, measured by memory. As the legendary engineer Patrick Hans said, code that works isn't enough. We need code that scales. This concept is the bedrock of our entire DSA series. It's what separates a hobbyist from a professional engineer. So, if you're ready to learn how to analyze your code and make it truly scalable, you're in the right place. Let's get started. To understand cost, we have to understand the single most important concept in optimization, the fundamental trade off. On the left, we have a linear search, time heavy. Imagine trying to find a specific book in a massive library by checking every single spine. It requires no prior organization, but it will take you a very, very long time. You're paying with your time. On the right, we have an index system, which is space heavy. Think of a library card catalog. It takes a lot of extra physical space, but it tells you exactly where to look. By paying with space to store that index, you save an incredible amount of time. This is the trade off you will make again and again as an engineer. You can often pay with space to save time. Keep this library analogy in your head as we go forward. Let's start with our cost analysis on a cheapest possible operation, the atomic unit, which is a cost of O1 or constant time. The computer knows what the computer is trying to do here is that the operation takes the same amount of time regardless of the size of your data. Accessing an element in an array is a classic example. How does this work? It's not magic, it's just simple arithmetic. The computer knows the starting memory address of the array, the index you want, and the size of each element. It just plugs these numbers into the formula. Address is equal to start plus index times the size. It's a single calculation. There's no searching required. Whether the array has 10 elements or 10 million, accessing one element by its index is an instant O of 1 of operation. This is the gold standard of efficiency. Next up is the cost ladder is the linear trap or O of n time. This is a checking every spine in the library scenario. When you're scanning a list for an item like Alice, in the worst case, you might have to look at every single element until you find it. The n in the O of n represents the number of items in your input. The graph shows this relationship perfectly. It's a straight line. If the input size n doubles, the amount of work you have to do also doubles. This is like finding a needle in a haystack. While not as fast as O of 1, linear time is often a very acceptable and common cause for many algorithms. The key is that the work scales predictably with the size of the input. Now we enter the danger zone. This is the quadratic equation or explosion, or O of n squared time. This is where operations grind to a halt and users get frustrated. The most common cause of O of n squared complexity is nested loops. When you have a loop running inside another loop over the same array, you are essentially comparing every single element with every other element. The growth here is not linear, it's exponential. As the slide here shows, you have 10, if you have 1000 items, you're not doing 1000 operations. You're doing 1000 times 1000, which is 1 million operations. If the input size doubles, the work quadruples. This scaling is unsustainable and is a major red flag in your code that you need to find a way to optimize. Cost isn't always obvious. Sometimes it's hidden in the language features we use every day, like string immutability. As we covered in our previous videos on strings, they are immutable, meaning they cannot be changed. Every time you see a plus operator to add to a string, You are not modifying it. You're creating a completely new string and throwing the old one away. This old string becomes garbage, abandoned memory that the system has to later clean it up. Imagine building a large string from many small pieces. A bad name approach using plus in the loop could create millions of temporary copies. A good approach, like using a list and the join method, might only create a few thousand. The lesson here is critical. Don't drown in copies. Be aware of the hidden cost of your operations. Okay, so we have seen the problems. Now let's build a toolkit to solve them. Our first tool for turning slow code into the fast code is a two-pointers technique. This is the master tool for achieving O(n) of time and with O(1) of space. Instead of using nested loops, we have two pointers, one at the start, one at the end, and we move them toward each other. This single pattern is the key to optimally solve a whole class of problems, including reversing the arrays in place without creating a copy, efficiently running palindrome checks, swapping the elements without needing any extra memory. It's an elegant, efficient pattern that should be one of the first thing you try or think of try for array and string problems. Our second tool is another brilliant way to avoid nested loops. It's called the sliding window technique. Imagine you need to find the maximum sum of any contiguous subarray of size 4. The naive O(n) square approach would be to recalculate the sum for every single possible window. That's a lot of repeated work. The sliding window approach is smarter. You calculate the sum of the first window once, then to get to the sum of the next window, you don't recalculate everything. You just adjust. As the formula here shows, the new sum equals old sum minus left element plus right element. You're subtracting the element that's leaving the window and adding the element that is entering the window. By just adjusting, you turn the quadratic problem into a linear one. O(n) square becomes O(n). Now we come to the ultimate tool for executing our fundamental trade-off, the hash map. This is how you pay with space to save time. The core idea is memorize to optimize. As you process your input data, you store it in a hash map. The hash map uses extra memory over fan space to create an index of your data. But what do you get for that space? You get instantaneous over average time lookups. Need to know how many apples you have seen? You don't need to scan the whole list again. You just ask the hash map and it tells you instantly. This is the go-to tool for a huge range of problems like frequency counts, finding anagrams, and any kind of fast lookups. Our final tool is another powerful space for time trade-offs, prefix sums. This is a pre-computation technique. Imagine you have an array and you know you are going to be asked for the sum of different ranges over and over again. Calculating the sum each time would be inefficient. Instead, with prefix sums, you do the hard work once upfront. You create a second array where each element is the cumulative sum of the original array up to that point. Now, if someone asks for the sum of the values from index 1 to 2, you don't need to loop. You can find the answer with a single subtraction, as shown here in the example. This allows you to answer any range query instantly in over one time. Let's quickly cover a special case you'll hear about in more advanced analysis, amortized analysis. Some data structure, like a dynamic array or an array list in Java, have an operation that is usually very cheap but is occasionally very expensive. For example, adding an element is usually O of 1, but every so often the array runs out of space and needs to be resized. A very expensive O of n operation where everything is copied to a newer, bigger array. The analogy is perfect. The rent is due occasionally because this expensive operation happens so rarely when you average its cost over all the cheap operations. The average cost per operation comes out to be O of 1. It is expensive rarely, cheap usually, and averages to O of 1. So, how do you apply all this theory to your own code? You use the analysis framework. This is your 5-step checklist to determine the cost of an algorithm. What is the input size n? Identify what n is. Is it the length of an array? The number of nodes in a tree? Second, count the basic operations. Look for the most frequent operations inside your loops. Third, drop constants. In Big O, we only care about how the algorithm scales. An algorithm that does 5n operation is simplified to O of n. Assume worst case. We always analyze the worst case scenario. If you're searching, assume the item is at the very end. Fifth, check extra space usage. Finally, look at how much additional memory your algorithm uses beside the original input. Follow these 5 steps and you'll be able to confidently analyze your code you write. This brings us to the complexity cheat sheet. The graph is your map to the world of algorithms. You need to know where your algorithm lives. O1 is excellent, instantaneous. O log n is great. We'll cover this with binary search. It means you can double your input and it only takes one more step. ON is good. Linear, predictable scaling. This is home of our two pointers and sliding window patterns. ON square is bad. The danger zone of nested loop. It does not scale. Your goal as an engineer is to always push your solution down this chart to find a more efficient algorithm whenever possible. To help you find that more efficient solution, here is the decision flow chart. This is a mental model for how to approach a new problem. Start by asking, can I solve this in one pass? If yes, you're likely in the world of two pointers or sliding window. Your solution will be O(n) time and O(n) space. If not, ask, can I trade space? If you can use extra memory to optimize, your go-to tool is the hash map. This will often get you an O(n) time or solution. If you can't solve it in one pass and you can't use a hash map, ask, do I need order? Often, sorting the input first is the key. Sorting costs O of n log n, but it can enable much faster logic forward. This flowchart is your guide to algorithm drinking. Finally, I want to leave you with this. Why do we care so much about this? Because complexity isn't just theory. It's a difference between working and waiting. An O(n) square algorithm to process a large log file could literally take 579 days to complete. Your user would be a skeleton waiting at the desk. The optimized O(n) algorithm could do the exact same job in 10 seconds. This is the real world impact of everything we have talked about today. And, that's a wrap on the cost of code. I hope this gives you a solid framework for analyzing and optimizing your algorithms. This is a cornerstone of our DSA series. If you found this valuable, please smash that like button, subscribe to our channel, and you have to ring that notification bell so you don't miss any of our next deep dives. And I want to hear from you. What's the trickiest algorithm you have ever had to optimize? Drop in the comments below. Thanks for watching, and I'll see you in the next one.